Alright, good evening and welcome everybody to N Simplex Pachinko. This is Obi-Wan Pez. Just hanging out and doing some more work on the Kolatz tree here. Figured I'd wait a few minutes, see if anybody else came in, but appears to be just me for the moment, so... Alright. I will be waiting for Matthew, who had a question. Hey, Fuzzy Jello, how's it going? Matthew had a question on mouse sensitivity, and I did a little bit of research, but probably not what he actually wanted. But we'll see how that goes. I'll ask for clarification when he comes in. So, uh, honestly, I have absolutely no idea. I was hoping for a couple of other little things, but let's see. Let's jump to the... I'm going to select something sort of at random here, as fitting with the name of the stream tonight. Oh, foul. There we go. Okay. The textures didn't quite pick up on the book I was opening. Alright, so let's talk about... transformation of functions, specifically with a mind to look at exponential functions. And logarithmic, why not? So, at some point in the past, I have talked about doing function transformations, but a lot of my students don't quite understand how ubiquitous these things are. Or at least how generalizable my particular method is versus something that they learn from, their high school teacher, which is mostly boiling down to you just plug some stuff into a calculator and get some numbers out. I don't rather enjoy that very much, but right, we can go like half volume. So anyway, most of the time what we see is that when we look at functions just in general, just again, some random function, well, okay. When we look at something like y equals 2 to the x, which is going to be our parent function for exponentials, or y equals log base 2 of x, which is our parent function for logarithmic functions, pretty much the most basic. What we're looking at here is that there's some sort of scheme that's going on that's just going to always be the same for this type of function, no matter what you do to it. So I said in like some of our previous sections when we were dealing with like polynomial functions, we do something like a quadratic. this could be rewritten something like this. So y equals 2 parentheses x minus 3 all squared plus 4 gets us this transformation of a quadratic function. And we can do the same with, you know, any other function that we want. We could do an radical. So square root of x can become something like y equals 2 times the square root of x minus 3 plus 4. And the fun thing about this is that this pretty much does the same stuff. The underlying function that is, you know, beneath this particular thing is different, and the general scheme of like what's happening to the individual values as they get plugged in is going to be slightly different. But the transformations of the parent function to the transformed function are going to be identical in both of these cases. So generally speaking, when we're talking about function transformations, we're looking at y equals a times some function of b times x minus c, all plus d at the end. And we talked about like what it is that all of these individual things do. So hey, Matthew. No, my actual students do not. Or at least they don't tell me. I imagine if they did find me, they would be like immediately jumping on it and being like, "What are you doing? How is this a thing?" I think the upper level students, the ones in like, you know, Calc 2 and stuff like that, would be rather interested in like, oh, that's kind of cool. The ones that are in my you know, liberal arts math classes would probably be like, what? Why are you on Twitch? There we go. Pretty much. Why is this old man here? I know this is riveting entertainment here. Sorry, just running in through my usual my usual Discord servers to say, hey, it's math night, because I screwed up and didn't do that ahead of time. Or like in the 5 minutes when I was doing stuff on the Colette's items. I could have been doing that instead. Anyway. So Matthew, I was telling the viewers at home and Fuzzy Jello that you had a question on mouse sensitivity, and I said that I kind of looked it up, at least tried to somewhat, and I didn't really know what I was looking for. So it's possible you will be unsatisfied with anything that I have to say about it. Okay, good. You want to share with me? Because no. No, I had it generally set for... Mm. I had it generally set to block, and, yeah. Really? Wow. That's crazy. Okay. I won't do that. I right-clicked your name, and it gave me, instead of, like, all the options, right-clicking your name made it come up with, like, a little graph for how long do you want to silence this person for? I'm like, nope, nope, mm-mm. And all the way at the top of the curve was ban. I'm like, well, no. uh, it's probably a setting that is deep inside of Stream Elements. It's probably not that deep, but... Mm, yeah, that's stuff with the... Alright, so I got like the bot stuff here. Oh, spam filters, there we go. So I can do like... Okay. Okay, so it's not Stream Elements. It must be actually Twitch. Stream moderation. Thank you. Oh, I see. Uh, let's try this. Maybe that'll work? Nope. Alright. Apologies. Yeah, no. It's... Alright, go ahead. Should be good. Wait, hang on. Do I need to hit save? No. Alright, try it now. Yeah, there we go. Whew. I mean, go for it. Just double check here. Yeah, that's alright to share. Really hope this is the right one. Nope, not seen a project. There you go. Alright, browser window. Boop. That's fair. Alright, hang on one sec here. There we go. Okay. So with your reversed contrast here. Alright, X is the inches moved by your mouse, Y is the inches moved on the monitor. Fair? Alright, so... Oops. Yep, makes sense. Too much jerkiness or whatever else, it doesn't really help. This is also why people turned off mouse acceleration, I believe, right? Generally speaking. Alright, fair. Yeah, it's the number of dots per inch, so one 800 DPI, for example, should be move 1 inch to move 800 pixels going across your screen, correct? Naturally, why we don't set... Yeah, no, that's fair. Mm-hmm. Yep. All right. Yep. Okay. It's fair. Between the coffee and my sweatshirts, man. Getting a bit warm in here. Mm-hmm. Yep, I got the field of view. Although I will say this is good for anybody who doesn't know what that is. Um, yeah, I started playing, well, let's put it this way. I started playing FPSs in Counter-Strike Beta 7. So, or rather, it was like Beta 5, and I remember the release of Beta 7. Yep. Yep. Sorry, I just had the thought. I don't know where my camera is. doesn't have... Sorry, doesn't have part of the retina. Yeah. Flipped on its side, I'm not really sure I understand. Right, fair enough. Rather than their retina. I gotcha. This may not be relevant, but why? Why is the retina vertical rectangle? So like programming wise, that's... They do it this way, and then it gets scaled out. Are you saying the coordinate system is done vertically? No, okay. That's fair. This is on me. Okay, fair. So okay, let's move this out of the way and go over here for a second and do this for a second. So what we're saying is that like you get your monitor that's like this, which shows you the shows you the very crude visualization of the world here. Right, and then all of this gets scaled down to, and this is a little ridiculous, I could have made this better, but whatever, it's fine. All of this gets scaled down to like a pinhole. And so the focal point is it like our actual eyes where there's like a lens that's further out, or is it saying that like your retina technically is in front of the focal point? Because that's going to be a little weird. So normally, right, this would... Oh man. This is going to be awful. Nope. That one would be here. This one would be down here. And so you'd have essentially this on the inside of your eye, but in a regular eye, like the tree would be on this side, the person would be on this side. And it's a curved surface, so it's all messed up anyway, but right. So in an actual eye, this is how it works, but in, you're saying computer land. Let's do this faster. This is essentially going to turn into this. This way? No. Okay, that's fair. Good times. Yep. You're gonna yell at me again. I mean, if this is what you're talking about here, where it's just basically like scaling down like that, then yes. Like I said, you're probably gonna yell at me again. Okay. Right. So then... formula. It's like 1 over f is equal to 1 over L plus 1 over R, or something like that, for focal length. That's probably something that you were not privy to or trying to get into, but there was somebody who was talking about this last time. Which, of course, not really that surprising. Well, this is a thin lens formula, so that may not may not apply to actually this situation, of course, because if we're not doing the actual lens thing. Let's see. L and R are the distances from this is like the object or objective distance, which is more of a photography term, I think, although that could be also just wrong, or I could be using it wrong. And R here is the relative distance to image. But anyway, it's so let's see, the actual focal length. The focal length here it's the right, so in terms of this, it's like the steady state where this distance is equal to this distance, I think. Anyway, not important. Anyway. So the monitor to the eye here is what you're saying? Diagonal. I didn't mean it necessarily along that, like along that diagonal line. Right, so like the distance to the center. Yeah. right? Which then has a image that I could dot out to like there. Which, again, I'm not going to do that at the moment, but okay. Yeah, I mean, probably not in that context. Um, although it might have some similarity. So the yaw value is like how you're when you're panning from side to side, right? So it's like a direct rotation along this particular axis. Uh-huh. Yep. How dare you? Radians per second. I'm guessing pitch is also going to be the exact same thing, but up and down. Uh-huh. Yep. Yeah, I guess. If they were going to stick with the yeah, if they're going to stick with the like flight analogy, then this one would be pitch and that would be yaw, but still, it doesn't matter. Especially since you just changed the direction that the yaw is occurring in, and then now it's, you just use the um, X and Y sensitivities to do a linear transformation. Or, sorry, linear combination of the two. Yep. I mean, I get the 3D space stuff at least, you know, because it's. I mean, this is the basis for a lot of linear algebra Calc 3 stuff, so. Yeah, so when you're rotating particularly this way, that's going to get you an axis which is normal to that particular curve for any particular rotation. Yeah. Now for the hard part, use quaternions. In doing particular function transformations in 3D space, in order to avoid the problem of gimbal lock, um, people have had to use things that are real numbers plus real I plus real J plus real K, where IJ and K are complex non-real. And are all orthogonal to each other. So you have to use 4D coordinates in order to do a lot of these calculations. Anyway. Anyway. Okay. Yeah, right. So that's going to cut through the, or the yaw circle lies on that particular plane. Uh-huh. Yep. Right. So specifically along here and along here. Yep, I got you. A lot of training in 3D visualization helps. Like continue these out. Uh-huh. So yeah, usually 70 to 120. You said 120 in this case. So technically, more like that. That's too small, but whatever, it's fine. It's totally 120 degrees. Yeah, it's just an angle. It's just we're changing what the distance across is by saying we're going further out. Yep. I literally started drawing it in before you started saying anything. Yeah, so these are 30, 60, 90 in the case of 120 degree um, field of view. Although it would be, yeah, it's a isosceles right triangles due to the fact that, or sorry, it's an isosceles triangle. We split it up into two right triangles. That leaves whatever this is here and this is here. These are going to be the same numbers, but it's going to be half of whatever is left over. Yeah. Yep. Yeah. What's H? I mean, doesn't matter, but oh, horizontal. Gotcha. It's all right. I'm flexible. These here, and then these here. These will be half the remaining amount, so this is going to be 180 minus the horizontal field of view over 2. Yep. Okay. Are you doing it? Building. Yep. All right, so pan. Or you could say it's technically not a pan, it's a rotation. Because it looks like a pan locally, but then when you put this out to like infinity, you're really seeing this as like seeing it as a rotation. Although you may not care about that. Mm-hmm. Not slash, but yeah, all of the angles are corresponding, so nothing actually changes in terms of the angle, but yeah. Jeez. Come on now. There we go. No. Nope. Nope. Man, nothing. Yeah, no, I mean it's fine. Like I've got a ruler I can use, but all right, so what do we get? I mean... Right, so if this is the object as it was, then like that would be the object where it is in the new position. Right, because the object's not moving. We're rotating our frame of reference. Um, that's a terribly drawn, but whatever, it's fine. Oh my god. Whatever, close enough. So if we've rotated our rotated our field of view, this is going to be our like delta theta. Yep. So this is going to be like focal prime, and our object has apparently moved this flat distance across our monitor. Yep. And again, this is still a right triangle. Having a little bit of a problem here. Because this appears to be a right triangle with the same focal length on both the leg and the hypotenuse, and that can't actually happen. Okay, so I think it's because the object is no longer on the... So I've constructed a right triangle here where f prime and f should be the same distance, but it's a right triangle, so the hypotenuse should be longer. Which means I did this wrong. It's like this should be drawn in an arc, right? And our like this and that should be the same distance. Maybe that's it. Maybe this is not important, especially for what you're going for. So if this is an actual rotation of delta theta, F now is longer due to the fact that it is further along the side of the triangle. It's no longer the altitude, which is the shortest distance. It's now a longer distance. Yeah. Okay. So like this position rotates. This is where the triangle is. Okay. Yeah. Got it now. You know, at times like this, I wish it would erase the whole line. Well, I mean, we want that direction anyway. So this is no longer here, right? That's still the same direction, but actually it's longer because the rotation causes this to be the same. It's F prime and F. Connected by an arc. The triangle is tangent to that arc. Okay. Okay. You know, Whiteboard actually did switch for a few glorious days there, and I didn't like the changes that were made because it basically made it much more like the Zoom Whiteboard, which kind of pissed me off. But there were certain features that were much better, and like having the option to just delete an entire line was pretty nice. Anyway. Okay, so the apparent location of it is going to be here. So the apparent movement is this now. Which also means that it looks... I see. That's going the other way for what I was thinking, but it's the same thing. So this would be the original position on the original monitor, which is now at the center of the monitor. So if you were like turning to look at something, then that's the original position on the upper monitor here, and that's its new position. We're actually focusing on it in the second. Or you could go the other way and say we were looking at something, and now it's been, since we've rotated away from it, it's now on this location in the old one, or on the new one. Yeah, one way or the other. We can pick whichever if we actually need to do calculations or anything. But you want that right triangle? Whichever one. Mm-hmm. Yep. Okay. So it's the opposite over the adjacent. The adjacent is going to be our like field of view, whatever that's going to be. Um, F or F prime, depending on which one you're doing. And then the apparent movement is what's going to be tangent delta theta is going to be equal to F over apparent movement. It doesn't matter which one you're looking at, right? It's either F or F prime. But we want the red. Right. So, oh. Gotcha. No, I'm looking at the cotangent. That was the problem. Oy. I just thought I was looking at the tangent. Anyway, yeah, so apparent movement over the focal length. I mean, so this is the tangent of dpi times rar. There we go. It just moved times dpi times yaw times the sensitivity x. Don't tell me you're using a tangent multiplication formula. Nothing. Alright, so like dpi times yaw times x sensitivity multiplied by x, our inches moved, is just going to be our variable. So then this is some sort of constant, which you could just call it like k. Yes, yeah, that's what I did. I just said that DPI, yaw, and sensitivity are all the constant. Like, you just smash them all together and make one constant. Um, it's somewhat disgusting, but you can get away with that. Mm-hmm. right? Because if you try to do inverse tangent, it goes on the other side, and then it blocks that one from being able to do anything. Yeah. It's the problem with relating to things like that specifically. Right. So it cannot possibly be linear. It's got to be a function of a tangent, which is always fun. Yeah. Right. And like I was saying on Monday when we were starting to like turn something, it was that the corner of the monitor especially would start to warp just a little bit. I'm imagining much for the same reason. I mean, that's fair. And not just a cylindrical curved monitor like you see nowadays with the yes. I mean, if you want to be like ultimately consistent, they should be a spherical cap essentially. So yeah, if you were to get something that is if you were to get a monitor that was actually a piece of a sphere like this. I mean, probably. So that's the other thing is that like this is actually what happens in your brain is that like there's this correspondence that's not working, but your brain compensates for it. And like all of the inputs that are coming into your eye are just inputs. So like if you were to actually remove the filters from your brain, which caused you to fail to see what you actually see, right? If you were to block the filters in your brain, this is like you would actually see the input that is coming in, unfiltered, and it could be weird. Um, yeah. So there's times where I've had dreams where like I don't know if this is actually what I saw, but like I was remembering something from like infancy or like maybe a modified version of it, but like there was weird stuff going on. I know that like my parents' voices were very muffled, strange noises that like like I said, I don't know if this is real or if it's just like a modification that came about through years and years of having like the same basic dream over again, but this is like a recurring dream that I've had my entire life, is that it like snapped back to this particular moment whenever it was, and I would hear my parents' voices in like this weird muffled sort of way. And it correlated to a very specific, like, you know, feeling that I had in my body. I don't know what exactly happened, but like, I would always, I mean, this is a weird thing, but this is always what happened when I had to wake up and go to the bathroom. Like, throughout that whole time when I was like, you know, 4 to 8, give or take, when it's like, when you're not entirely trained 100% to like still get up when you need to get up in the middle of the night. Misakide, how you doing? We're talking about weird stuff, so feel free to feel free to interject if you're interested, or if you have anything else that's going on here. But yeah, it was always like this weird sort of. Thank you for the follow. And yes, the 80s arcade music, always the best. So, oh, sorry. See, this is the problem. I can't hear it because it's playing only on your side. When I had it playing, it really got screwed up somehow. Overlays. Ah, wait a minute. I can just turn down stream elements. I have heard the word before. Ah. Okay. Polytopes may exist in any general number of dimensions. So, I mean, technically, my channel name has something to do with it. Yeah, so I work with, or I have been working on some research that had to do with specifically the N simplex, and so that was the whole place where my channel name came from. That's nasty. I'm not looking at what I'm drawing. That's the problem. And again, this was specifically looking for, like, you know, the individual paths that would get you from point A at the top to point B somewhere in the middle here at the bottom layer of the simplex. Yeah. But I haven't done a huge amount of work. Okay. So I think that I have now fixed the volume on stream elements. No, not gallery. My overlays. That one. Okay, it's probably going to throw a temper tantrum because I'm currently running the stream. But anyway. Right, so I like halved the volume, so hopefully that'll be not distorting itself. So, Misakide, are you doing some work specifically with polytopes, or just curious? Like I said, I can't necessarily promise that I've got the information you want, but we can try to work something out. You're really not gonna like Quaternions. That's not what I want. No, I didn't just screw myself over. Cool. Ah, very nice. They have all sorts of crazy names. They don't have to, obviously, but... Yep. Yep. The y over the focal length multiplied... Oh, is this your zooming? Mm-hmm. It didn't let you say the name? Oh, does it have some sort of banned word inside of it? Yeah, I'm having a problem seeing it. Where is it? If you increase focal length, it's the... Gotcha. Okay. So if we increase the focal length, our tangent value comes down. or if the tangent has to stay constant, the all right, fair. If you increase the focal length. All right, so you're like stepping away from the object and making it look smaller. Can you really not say shit in here? Eh, worked fine for me. Must be a profanity filter somewhere that I just left on. Auto mod rule set. Okay. Yeah, no, that's fair. Profanity, I have less filtering on, so yeah. Alright, whatever. Alright, anyway. Wow, I just showed you all that. Oh. Brilliant. Alright, do I need to destroy something? No. No. I mean, it didn't really matter, right? Because it was just me clicking through a couple of things. But it doesn't, like, I didn't see my stream key or anything. The only note, yeah, my notification was the only thing that was like remotely. It's not hidden or anything. Anyway. Alright, anyway. Okay, yeah. Uh, just found. Yeah, some of the names for these. All right. Well, that's weird. So it says in this is like March of 2020. It was the Polytope Discord. Um, had the names that you're talking about. So All right, I did run the play button on one of these earlier, but let's see. Yeah, the DPI. So if you bring down the DPI, this is going to extend out further. We end up having a slow or a low tangential value. Right. So the apparent distance versus the focal length decreases, means the focal length must be increasing, relatively speaking. Okay. Ah. Oh no. Return. There you go. Let's go between 0.01, 0.03. Okay. So it doesn't appear to be like a huge, like relatively, they appear to be moving quite a lot similar to each other, at least for values close to 0.03. Values closer to 0.01, they start splaying a bit more. Okay, so yeah, I guess what's what's the appropriate XY window? Oh, nice. 10th to join the Polytope Discord. So that's the Y values. And X values were between 0 and like 8. Since that's about the size of my mouse pad. Almost 2,000 members. Awesome. So, I mean, like, DPI has much larger effect on it, but at the same time, you're probably not going to get a... Probably not going to have a DPI lower than, like, I don't know, 50? Realistically. Right, and if you have a really low DPI, it's going to stay really tight, but at the same time, it's just going to be miserable. Or are you talking tight to the y-axis? I mean, you can make it really sensitive or really insensitive, and again, they all get really close to each other, but that doesn't necessarily mean that's good. Hmm. base and, right, just 1x. Yep, no, I got you. This one. Mm-hmm. Right. So if we turn it up some, 1.05, we get an equal amount somewhere pretty close to 4, but it's also split the opposite direction right at the beginning, albeit a small amount. Hmm. Right, so that small movement is not exaggerated too much. Certainly would seem so. Okay. Let me turn off 1, turn it to 2. Again, here you get much more deviation. Do you also get to change the sensitivity for every multiplier? Or for each zoom level? Or is it just the adds multiplier? Yeah. Uh-oh. Uh-huh. Right. Okay, yeah. So now you're way off. You're over here somewhere where this difference is humongous. I mean, comparatively. Mm-hmm. So you're going to go like this. Do the multiplier 1.2 when you're really far out. And then when it's really close, it's going to be a little bit... No worries. Also true. Hopefully they're not jumping right in front of you when you are zoomed in, because that always gets distracting. Not them specifically, but somebody else. It's always fun. But something else that I just thought about, if typically the region that you're looking at on your screen is also going to be restricted, usually, correct? So like most of the time the stuff around the outside will still be either black, as it is in Team Fortress, at least used to be, or they'll have it be like a blurred out version of the background that you had beforehand. So then when you're moving in 10 times scope, you're only moving this much, while the distance is moving significantly. It's moving significantly at distance. Yeah. I don't know how Apex does it, just because I haven't played that game. But so is 1x basically iron sights. Like it's a zoom, but it's not necessarily a zoom. Yeah, that's like 1.5 or something. Alright, that's fair. Oh, is it a red dot? So you look through and it's just like dot sight? Yeah, okay. I used to play airsoft, so like these were all options that we had naturally. Um, so one of my friends really liked doing red dot sights on his I think it was an M16. Just because he could get like a long distance, but at the same time, it wasn't really. It is not a sniper rifle. So he had an M16 replica, and so he would, get on the ground and, yeah, he loved the red dot sight. I thought it was pretty good, but I never went with it for mine. I had like a, I don't know, 5-time sight or something like that. Oh, no, adjustable. I had an adjustable for my actual sniper rifle, and then I had a 2 times, I think, for my Stayer AUG. So I love the AUG. I was a Counter-Strike player originally, like I said. So it was a lot of like I definitely want to have this gun because it's just that much. It's just awesome. All right, what do we got? So like whether or not you're zoomed in, you'd turn exactly the same amount. That would be insane. Like I kind of like the idea of being zoomed in and not having to be like, "Oh no, there's someone behind me," and like having to zoom out and then turn, but you have to take your face off the uh, scope if you want to actually turn around and shoot somebody. Yeah, that's nuts. That doesn't even seem fun. Yeah, I feel like you could have a paper in that if you actually formalize it. Yeah. That's fair. I didn't mean like necessarily a paper for Apex. I just meant like, you know, if somebody wanted to actually write up the mathematics for this in terms of like how this stuff is related to, generally speaking, zoomed in, you know, zoomed in points of view, it could potentially be there. Yeah. But yes, if you want to keep it to be for fun and not make it work, then probably, yeah, that would be a good idea. All right. See you, Matthew. Have a good one. I'll see you Friday for, possibly anyway. See you Friday for Mortalis Principle. How trigonometric functions are calculated. Oh boy. You mean from a computer standpoint, right? So like how I would calculate tangent of 40 degrees is actually based on, well, there are a few different ways to do it. One is calculus, and it's fairly simple to do. And I mean, I can give you the two second primer, and then we'll talk about it actually next time. But basically, you got a tangent function that looks like this. This is our 0. Let's say 45 degrees is here, with a slope of 1, which, you know, not exactly, whatever, it's close enough. But I only know, right, this is the thing, is I only know what the value is at 45 degrees, or 0 degrees, or 30, or something like that. If I want to calculate what it is at 45, sort of. Oh, sorry, if I want to calculate it at 40 degrees, so this is going to be f at 40. Basically what I'm going to be doing is just doing the I'm just going to be doing a linear approximation and saying that this is going to be the slope right? I'm going to, well, not equal to, it's going to be approximate, but it's approximately equal to the slope of the tangent line at 45 degrees. And then I say, you know what, it's close enough. So we'll solve for this, and again, this is going to be like a 5. Here we're going to add f of 45 to the other side, and then it just does a calculus stuff. So it's not like a huge deal. So the values of tangent that I know offhand are just going to be the basic ones, where it's 0, 15, 30, 45, 60, 75, and 90. Now, actually, 15 and 75, I don't know offhand, but I can calculate them. It just takes me a minute, because this is going to be the sine of 15 over the cosine of 15. And I know that the sine of 15 is calculated using either a half-angle formula or a half-angle formula or a sum and difference formula. So this is going to be, so again, I know offhand that this is going to be the square root of, calling myself out here, 2 minus square root of 3, no, not that one, hang on, square root of 6, sine is small, so minus the square root of 2 divided by square root of 6 plus the square root of 2. So I know offhand that the sum and difference formulas are going to get me these values. Technically, it's over 4, each of them, but again, it's in a ratio, so it just divides out. It's fine. In terms of like 30 degrees, what do I do with it? I just make a 30, 60, 90 triangle and say this is 1, 2, and root 3, and you know, tangent of 30 degrees is going to be 1/2. So if I want to get in there and like prove it, that's an equilateral triangle. Trust me, it totally is, even though it doesn't look like one. So 30, 30 makes 60, 60, and 60. So like the values around the outside of the unit circle, right? This is how I'm calculating it, is I'm making equilateral triangles, which then give me this thing, which then I can use as a template to say, I'm going to put it this way and that way and this way and that way. And then into each quadrant, I've got 2 different arrangements that make it work. And then I also do the same for 45 and say, okay, well, this is going to be 1, 1, root 2. And then I'm going to do the same thing here. I'm going to scale this up and down as I need it to. It'll fit inside my unit circle, do these 45-degree angles in every quadrant. There's those. So like not all the rest of them, but most of the rest of them, yes. So if you want a specific one, so again, 40 degrees, then I don't know any specific properties that like a 40-degree angle has with its side lengths. I just don't know any. There are others, right? If you can add, subtract, multiply, divide all of our known values to get any of the other ones around the unit circle, then we can come up with something, you know, directly related. Like, you know, sine of 15 degrees, root 6 minus root 2 all over 4. Right, is the sine of 60 minus 45. Yeah, that'll work. Or a few other ones. Anyway, yeah. All right, See you later, Matthew. Have a good one. Alright, so if anybody happens to stumble in. What I've been talking about before was what happens when we have, transformation of functions. Again, just generally speaking, if you're doing transformations of functions, we have this template here which tells us what to do in every single case. We have the vertical stretch factor. We have the horizontal compression factor. We have the horizontal shift. And we have the vertical shift. All right, so each of these things is a linear transformation. So you're multiplying something, or you are adding, in this case subtracting, but again, addition, subtraction, they're the same thing. The horizontal compression factor is telling us that we are going to compress this by a certain ratio, so it's going to be crunched by that certain amount. So in the case of an exponential function, again, y equals 2 to the x is kind of what we consider the most basic. Then we're going to say here, we pick a value, let's say x is equal to 0, gets us this nice y equals 2 to the 0 power. So 2 to the 0 is going to be 1. And then every time we move over 1, what we're going to be doing is doubling the vertical distance. We're just multiplying the vertical distance, which is y, by 2. So here we move over 1, we double that distance, it becomes 1. Move over 1, we double that distance, oops, becomes 2. Nope, that becomes 4. It's 2 blocks, but it's a distance of 4. I should really write this out. Right, make sure your axes are here. 6, 8, 10, 12, okay. Alright, move over 1, double this distance. Again, 4 blocks becomes 8. Move over 1, double 4 blocks. 4 becomes 16. And we're right up at the top of the thing here. And again, if we want to go left, we do the same thing. You move left, it's going to cut our vertical distance in half. So this now becomes a half. Over 1, halve the distance again, becomes a quarter. Over 1, halve the distance again, becomes an eighth. And then we draw this in. All right, looks something like this. And then we go over here and we do the same thing with the logarithm base 2. So log base 2 is, you could also say this is the inverse function of the exponential with base 2. Or you say, again, what exponent on a base of 2 gets me this x value, which is going to be our exponential. So in this case, having a base of 2, I just completely lost my train of thought there. It's fine. In order to get an x value of 1, which in this case, we're going to make our x values here the scale is going to be 2 going across. And 1 going up and down. Goodness. I hope that doesn't stick around. Anyway. Alright, so anyway, as we increase our y value, which is our exponent, we're going to increase our x value as the exponential. Or you increase your exponential from now 1 up to 2. We can use powers of 2 to make nice exponent values. So getting a 2 in our exponential is having a 1 for our exponent. Having a 4 for our exponential is the same as having a 2 for our exponent. Having an 8 for our exponential is the same as having a 3 for our exponent. And so on and so forth. 12, 14, 16 to 4. Going up there. Kind of a mistake, but alright, it's fine. And then we could do the same thing going the opposite direction. So we're going to decrease our exponential to a half, which gets us an exponent of 1 on a base of 2. Negative 2 for our exponent, well, other way. So again, getting our exponential to be 1/4, so halve the distance again. It's going to make an exponent of negative 2. Halve the distance again. Exponential is 1/8. That gets an exponent of negative 3. So I'll get this like this. We get stuff going like this. Alright, then we also have our asymptotes going like this. This one is y equals 0. And here this one is x equals 0. Okay, so if we want to apply the same transformation that we did over here to our on our quadratic and square root functions to now the exponential and the logarithmic functions, we can do that just the same. So if we want y equals 2 times 2 raised to the, I'm going to regret that, x minus 3 plus 4, let's change the 2. It's a little silly, right? If we have the same base as we do multiplier out front, it's not really going to do much. Let's make that just 3. So what we see is that, wait, I can copy this, can't I? Really? Okay, well, I guess that's going to just be stuck on then. That's cool, whatever. So if I select all this stuff, copy it, and then choose to paste it over here. No idea if this is going to work. Okay, cool. No. Alright, I need to select everything again. good enough. All right, so what we're going to see with this is that we're going to take our original function, which is just y equals 2x, and we're going to do these shifts first, which is what I recommend. Now, in the case of an x minus 3 in the exponent, what you're saying here is this is, again, a horizontal shift. This is the same as our x minus c that we see in the general form. So x minus c is telling us that this is going to be a horizontal shift. How does that work exactly? Well, if you think of it in terms of like what this is really doing, we're taking whatever our exponent is and we're subtracting 3 from it. So we're saying like, okay, treat the value at x equals 0 as if it had an exponent that was 3 smaller. So we go over here, we find the value that's 3 smaller. So this is x equals -3. Our y value for that is 1/8. And then we say take that value and translate it back over to x equals 0. Right? Or in other words, if you plug 3 into the exponent, you're going to get a 0 for an exponent. So then we'd have to go 1, 2, 3 all the way over here before we hit this particular value. So this is why it's shifting to the right when you have a minus something in the exponent or in the within the function. All right. All right, this is going to piss me off. So let's get this thing actually centered. Or at the very least put on a line. Okay. But then we also have this value here, which is going to take all of our functions' outputs and just move them up 4. So our 0 value in this particular case is the asymptote, y equals 0. So our 0 value of y equals 0 is going to get shifted up 4 spaces. So then we're going to have an asymptote here at y equals 4. All right, and our initial point is this one that I always like to talk about. Right, our origin point, which used to be at 0, 0, is now getting shifted up 4 and to the right 3. So it's here. Now there's nothing actually there, right? This is just an empty circle. It's where the asymptote is. But I like to include that. All right, so the initial point is going to be, again, at a distance of 1 here. In the new function, our vertical values are all getting stretched by a value of 3. So here, our distance is going to get tripled. So instead of being 1 up, it's now going to be 1, 2, 3 up. And it's going to be here. Now, if you don't believe me, that's perfectly fine. All we have to do is go over here and say, okay, what do we get when we do this? Well, if you plug in 3, this gets us an exponent of 0, which then eliminates the 2 to the power term, right? It eliminates our exponential term. So we just get 3, which tells us that this will be a distance of 3 away from 4. So a distance of 3 up away from 4 puts us at 7. So that's what we see here. We're at 7. And again, how do you get this thing, this term here, the 3 times 2 to the x minus 3, how do you get that to all be 0? How do you reach the line y equals 4? And the answer is you don't. You can't get an exponential 2 to a power that's going to be equal to 0. So that's why we have an asymptote at y equals 4 now, instead of y equals 0 before. We're just looking at this term and saying, what does it take to get this term to be equal to 0? And again, you can't. Okay, so this is our initial point here. Again, 3, 7. All right, then we say, based on that, we're going to say the next point over. All we really have to do here is say what's going to happen to this term, which is, again, the distance term. This can be thought of as kind of like our base term. Not to be confused with that base, sorry. Let's back off here. Yeah. We won't give it a different terminology or anything like that. So I like this as like the base term. We're going up this distance, and then we're basing all of this off of the distance from that location. So when we look at the distance from that location, we're saying here, we start from our origin point. We have a distance of 3 to go up to get to here. And if we move 1 away to the right, then what this is going to do is it's going to increase the exponent by 1. Well, when you increase the exponent by 1, our distance gets doubled. So now instead of a distance of 3, we're going to have a distance of 6. 2, 3, 4, 5, 6. Or the distance gets doubled. And if we move 1 back to the left, our distance here between the asymptote and where we were gets halved. So here we're going to go half of 1 and a half of that distance. Half of 3. I should really be careful with this. This is a distance of 1, 2, 3. We're going to halve that, and now it's going to be 1 and a half. It's going to be here. 1 more to the left, it's going to be half that distance. So 0.75. 1 more to the left, it's half that distance. 1 more to the left, it's half that distance, etc. And again, 1 more to the right. From this distance of 6 here, we're going to have a distance of 12. That'll put us here. Way up. But it really is kind of that easy once you start thinking of this in terms of relative distance, rather than being absolutely married to this concept of needing values and numbers to pick. It also ends up getting you a much more intuitive sense of how this all works when you start thinking of, okay, it's the same pattern as before. All we have to do if we move over 1, in this case, is, again, double our distance. All right. There's a lot more I could do here. At any rate, we are going to raid over to somebody else. Jason Charles Miller is on. Boss Lady B is on, doing exobiology. Dev is on, doing DBD. So, I had mentioned Buana the other night. We raided him, and his wife Safia was on. They are continuing their goal to get to New Year's They have done it so far. Continuous stream minus a few breaks here and there. So congratulations to them for doing a really good job with it. Let's go raid Dev. I don't know if he's gonna duck out. He needs to go to bed, honestly. Stream manager. All right. So, again, thank you everybody. Have a good night. We'll see you again on Friday for more Talos Principle, and ought to be good. It's in extremely poor taste, but at the same time, the message of it kind of needs to get out there because it's a really awesome game. Alright. Good luck. Stay safe. Have a good night. See you Friday. This is Obi-Wan Pez for N Simplex Pachinko. Good night.